some tags. Only got $20 in my pocket. I'm hunting, looking for a come up. This is fucking awesome.
Define pressure and discuss pressure at point through illustration and formula derivation. A physical force that we exert on an object refers to a pressure. The force that being applied to this object is perpendicular to the surface of the object per unit area. Pressure unit is newtons per square, which we also call pascals. Pressure is very broad and has a different types. These are atmospheric, absolute, gauge, and differential pressure. The formula for pressure is P equals F over A, in which F is force on the object and A refers to the area in which the force acts. Besides, we also measure the pressure of the gases and liquids in certain conditions. The pressure or liquid has to equal the density of the fluids multiplied by the acceleration due to the gravity and height of the fluids above or a certain point. Express and illustrate Pascal's law and give a real-world example of it. When pressure is applied at any point in the fluid at rest, the pressure is equally transmitted in any all direction and any other point in the fluid. Hydraulic jack and hydraulic machines are based on the Pascal's law. So here is the example. Assume that two hydraulic cylinders of different areas are connected. Since both pistons are at the same level, pressure remains the same.
The question for number 3 is illustrate how pressure vary with height. Cite real example in which this concept is fully illustrated. So this one tackles with pressure and height, and pressure decreases with increasing altitude. The pressure be interpreted as the total weight of the air above a unit area of any elevation. Then the example for this one is a mountain climber on Mount Everest. When climbing, a mountain climber can feel that his body is being expanded due to the low air pressure that pushes less against the body. Then expand tissues can put pressure on joints that can cause pain. So for number 4, when density is relatively changing with height, what will happen to the change in pressure between 2 points? Cite an example to the best that explain your claim. So, the higher the density of an object that is exerting in the pressure, the higher the pressure of an object in which the pressure is being exerted. Because it follows that the higher the pressure exerted on an object, the higher will be its density. The example of this is a thumbtacks being pushed or pressed on a ball. If you apply pressure on something by pushing on it, the thumbtacks or the object, the part that you're touching, compresses, making it more dense.
So, the water in a tank is pressurized by air, and the pressure is measured by a multi-fluid manometer as shown in the figure. Explain the process measuring the pressure at point 1 or the gauge pressure of air in the tank. So, we assume that the air pressure in the tank is uniform, meaning its variation with elevation is negligible due to its low density, and thus we can determine the pressure at the air-water interface. So starting at the pressure at point 1 at the air-water interface and moving along the tube by using the barometer equation or top plus quantity G over G sub C times the height or the PGH terms, in which adding as we go down or subtracting as we go up until we reach point 2 and setting the result equal to P atmospheric since the tube is open to the atmosphere. And we need to remember that the gauge pressure is equal to the P absolute minus the P atmosphere. Also, we need to remember that pressure gets larger as we go deeper. So, since the tube is open to the atmosphere, gives P1 plus P water GH1 plus P oil GH2 minus P mercury GH3, which is equal to the atmospheric pressure or P atm. So, solving for the P1 or the gauge pressure of the air in the tank from point 2 or the atmospheric pressure down the height of H3, so the pressure gets larger. So we're going to add PGH terms, which is mercury. That's why we have plus P mercury GH3 there. Then from the height of mercury, so from there going up to the height of H2, which is oil. So since we're going upward, the pressure gets smaller, so we're going to subtract P oil GH2. That's there's P negative P oil GH2 there. So from there, the height of oil, which is H2, going upward to H1, which is the height of water. So since we're also going up, we're going to subtract P water GH1. So the equation becomes P1 or point 1 or the gauge pressure of the air in the tank is equal to P atmospheric or the point 2 minus P water GH1 minus P oil GH2 plus P mercury GH3.
Define and explain thoroughly what fluid statics is all about.
So the branch of fluid mechanics that studies incompressible fluids at rest refers to fluid statics. In comparison to fluid mechanics, di ba fluid mechanics is a study of fluids in motion. Ang fluid statics involves the study of the conditions under fluids nga naa sa rest in stable equilibrium. Fluid statics is generally referred to as hydrostatics and aerostatics. Mayon tag hydrostatics kung ang fluid kay liquid. Mayon tag aerostatics kung ang fluid kay gas. So, di ba, fluid statics refers to fluid at rest. So, kaning fluid at rest, it has no shear stress. Consequently, nalag ka-develop nga force, but it is just due to the normal stresses such as pressure. Like, for example, kanang masalom ta sa ocean or sa swimming pool, the more ta naa sa ilalom, the more kanang heavy atong kakabati, di ba, sa atong ulo. Like, kanang gusto siya mag-explode, atong dalunggan, inana. It is because tungod sa weight sa water nga naa sa atong ibabaw nga more mo press down sa atong body. So mo na siya, and such condition is termed the hydrostatic condition. So asa din common ginagamit ang fluid statics? So fluid statics are used to describe the forces that operate on floating or submerged bodies such as sa mga barko, sa mga submarines, and other forces nga kanang mga hydraulic presses and carjacks. So kani mga designs sa mga engineers such as engineering systems, mga water dams, mga liquid storage tanks, ga-require ni siya nga ma-determine ang forces nga ga-act sa surface using fluid statics. So di na to may buuan ng mga pressure sa water dam kung unsa siya kakusog ang kuan sa water kung walay tabang sa fluid statics. So the resultant hydrostatic force acting on a submerged surface like mga submarine, mga barko, it requires determination of the magnitude, direction, and most especially ang line of action sa force.
So for question number 7, on a plane surface, the hydrostatic forces form a system of parallel forces, and we often need to determine the magnitude of the force and its point of application, which is called the center of pressure. The figure you can see is an inclined plane surface completely submerged in a liquid. The plane of this surface intersects the horizontal free surface at angle theta, and we take the line of intersection to be the x-axis. The resultant hydrostatic force acting on the surface is this equation, which is F is equals to P naught times A plus density times gravity sine theta integral of y dA. But the first moment of area is related to the y-coordinate of the centroid. So the formula for this is yc is equals to 1 over a integral of y dA. Substituting this formula to the equation of the resultant force, then we have force is equals to pressure of the centroid times area. Therefore, the magnitude of the resultant force acting on the plane surface is equal to the product of the pressure at the centroid of the surface and the area of the surface. And for the center of pressure, it is the point where the resulting force's line of action intersects the surface. To determine the center of pressure, we combine the equations of the vertical location of the line of action and second moments of area about two parallel axes. So we get the final center pressure formula into yp is equals to yc plus I sub xx over yca.
Number 8. In the illustration shown below, explain how the magnitude of force and the center of pressure was determined in a submerged curved surfaces. The easiest way to determine the resultant hydrostatic force Fr acting on a two-dimensional curved surface is to determine the horizontal and vertical components Fh and Fv respectively. In this illustration, we can see the Fh and Fr inside the circle. The horizontal component of a hydrostatic force acting on a curved surface is equal to the hydrostatic force acting on the vertical projection of the curved surface. On the other hand, the vertical component of the hydrostatic force acting on a curved surface is equal to the hydrostatic force acting on a vertical projection of the curved surface plus the weight of the fluid block. This is the formula of hydrostatic force of the liquid. It is equal to the square root of the sum of the squares of Fh and Fv respectively, while the angle is equal to the Fv and Fh respectively. The exact amount of the line of action of the resultant force can be determined by taking a moment about an appropriate point, whether they are above or below the liquid. Note that in case of a curved surface above the liquid, the weight of the liquid is subtracted from the vertical component of the hydrostatic force since they act in opposite directions. Thank you!
So guys, based from question number 9, discuss the buoyancy and stability concept and cite real life in which this concept is fully explained or illustrated. So let's start. Concept of a buoyancy or upthrust. It is an upward force exerted by a fluid that opposes the weight of a partially or fully immersed object. In a column of fluid, pressure increases with depth as a result of the weight of the overlying fluid. Thus, the basic concept is very simple for anything placed in a fluid medium. The upward force the medium exerts on the body is equal to the weight of the fluid that body displaces. This is not only true of bodies placed in water, since it is also true of those in air. But the weight of air displaced is usually not enough to float the aircraft. Though buoyancy is a fairly straightforward concept, although it may be a little hard to grasp up front, stability is the ability of the ship to resist overturning. So here it is, guys. So this is a concept of stability. If the point M is at the G, it is a neutral equilibrium. And if the point M is above G, it is a stable equilibrium. While if the point M is below G, it is an unstable equilibrium. So you can see it clearly in the picture. Another one is the concept of stability can also be illustrated in a cone placed on a horizontal surface. So that would be all. Thank you.
So for question number 10. So first, let's define metacenter. So metacenter is a point intersection above the center of the gravity of the shape and the new center of buoyancy when a body is tilted. It is to ensure its stability. Next, metacentric height. So, metacentric height is a measurement of initial stability of a floating body. So, in other words, metacentric is the measurement between the center of gravity of a ship and its metacenter. So, metacenter and metacentric height is important in floating bodies. So, having your metacenter at the top of your center of gravity ensures stability, and the larger your metacentric height implies greater initial stability against overturning.